Dragon's Gambit. Strategic Intelligence Analysis, Episode 2. Part 4. The Path to Independence, What a Genuine Strategy Looks Like. Not the political speeches. The engineering and the economics. Why just mine more is insufficient. The political instinct, in the United States particularly, is to frame rare earth independence as a mining problem, identify deposits on American soil, permit the mines, and the dependency is resolved. This instinct is wrong, and understanding why it's wrong is essential to building a strategy that works. The United States has significant rare earth deposits. Mountain Pass in California, which is currently producing, is one of the largest rare earth deposits in the Western world. There are deposits in Wyoming, in Alaska, in North Carolina. The resource is not the problem. The problem is processing and magnet manufacturing, the two steps that follow mining and that represent 85 to 90% of the value added in the rare earth supply chain. Here is what a domestically mined rare earth deposit requires before it becomes an F-35 actuator. Step 1, or concentration, crushing, grinding, flotation, and magnetic separation to produce a rare earth concentrate. Capital cost, significant. Environmental permitting, complex. Timeline, 3 to 7 years for new facilities. Step 2, hydrometallurgical separation, the solvent extraction process described earlier, hundreds of stages of liquid-liquid extraction using organic solvents and acids, producing individual rare earth oxides with purities of 99.99% or higher. Capital cost, substantial. Skilled workforce requirement, highly specialized chemical engineers with specific rare earth experience. Environmental permitting, extremely complex given radioactive waste streams. Timeline, 5 to 10 years for new facilities, including workforce development. Step 3, metal production, converting rare earth oxides to metals through molten salt electrolysis or metallothermic reduction. Capital cost, significant. Technical complexity, high. Timeline, 3 to 5 years for new facilities. Step 4, alloy production, combining metals in precise ratios to produce NdFeB or other magnetic alloys. Timeline, 2 to 4 years. Step 5, magnet manufacturing, sintering, machining, coating, magnetizing, and quality testing of finished magnets to defense specifications. Timeline, 3 to 5 years for new facilities with appropriate quality systems. Total timeline from greenfield to production, 10 to 20 years for a fully integrated domestic supply chain built from scratch, assuming no regulatory delays and continuous funding. The United States does not have 10 to 20 years of runway before the supply chain dependency creates operational consequences. It has years, not decades, to build interim solutions while longer-term infrastructure develops. What is actually being built? Status June 2026. The picture in mid-2026 is one of accelerating investment against a genuinely difficult timeline. Mountain Pass, MP Materials. The Mountain Pass mine in California, operated by MP Materials, resumed rare earth concentrate production in 2018 after Molycorp's 2015 bankruptcy. As of 2026, it is producing light rare earth concentrate, primarily lanthanum, cerium, and praseodymium. The critical development, MP Materials has been constructing a rare earth metals and magnets facility in Fort Worth, Texas, in partnership with the Department of Defense. This facility is designed to produce NdFeB magnets from domestically separated rare earth materials. Milestones as of 2026, the separation circuit is operational, the metals and alloy production is in commissioning. Magnet production is targeted for full-scale output by late 2026 or 2027. Current production capacity, sufficient for a fraction of U.S. defense needs, scaling. The significance is the establishment of the manufacturing knowledge base and quality systems, the technical capability, that can be scaled up with additional investment. Lynas USA, Texas. Lynas Rare Earths, the Australian company with the largest rare earth operation outside China, the Mount Weld mine in Western Australia and the lamp processing facility in Malaysia, has been constructing a rare earth processing facility in Seadrift, Texas, funded in part by Department of Defense contracts. This facility is designed to produce separated heavy rare earth materials, including dysprosium and terbium, which are currently not being produced domestically at any significant scale. Heavy rare earths are the most strategically critical and the most dependent on Chinese processing. Status as of 2026, construction progressing, with initial production anticipated 2027 to 2028. Full-scale production pending regulatory completion and workforce development. Defense Logistics Agency stockpiling. The National Defense Stockpile, which was largely drawn down during the 1990s budget reductions following the Cold War, has been receiving renewed investment to rebuild buffer inventory of critical rare earth materials. The specific quantities are not publicly disclosed, but the budget line items are visible in defense appropriations and indicate sustained investment in inventory building since 2020. The NdFeB magnet problem. The most critical remaining gap in the domestic supply chain is NdFeB magnet manufacturing at scale. As of 2026, the United States produces essentially zero NdFeB magnets domestically at the scale required for defense applications. MP Materials' Fort Worth facility represents the beginning of a solution, but full domestic sufficiency for defense applications remains several years away under optimistic assumptions. The Allied dimension, why this cannot be solved unilaterally. The United States cannot build a complete rare earth supply chain independence from China on its own within the relevant timeframe. The realistic path runs through allied supply chains. Australia. Australia possesses the world's sixth largest rare earth reserves and, through Lynas, the only significant rare earth processing capability outside China at the moment. The Australia-US Critical Minerals Partnership, formalized under AUKUS-adjacent industrial cooperation arrangements, is the most important bilateral rare earth cooperation relationship in the world. Australia's Northern Territory has significant rare earth deposits, the Nolans Project, Arafura Resources, the Dubbo Project, Australian Strategic Materials, and others, in various stages of development. The Australian government has designated rare earths as a critical mineral with national security significance and has provided financing support for domestic processing development. Canada. Canada has significant rare earth deposits, particularly in the Northwest Territories, Nekalacho Project, Cheetah Resources, Quebec, Gaspé Project, and British Columbia. The Nekalacho Project produced the first rare earth concentrate in Canada in 2021. Canadian federal investment in critical mineral processing is accelerating. The U.S.-Canada Critical Minerals Working Group under the USMCA framework has identified specific cooperation priorities including rare earth processing. Japan. Japan is the world leader in rare earth magnet manufacturing, or was, before much of the production capacity relocated to China following the 2010 supply disruption. Japanese companies including TDK, Shinetsu Chemical, and Santoku retain world-class technical capabilities in rare earth processing and magnet manufacturing. The Japan-US Economic Security Alliance includes explicit rare earth supply chain cooperation, with Japanese investment in alternative supply sources, including partnerships with Australian and Canadian producers, and U.S. cooperation on processing technology development. The economics: why market forces alone are insufficient. The rare earth supply chain problem cannot be resolved by market forces alone. This is not a political statement, it is an engineering and economics reality. The cost disadvantage is structural. Chinese rare earth production benefits from state subsidies that do not require market returns, environmental and labor standards that externalize costs Western producers must internalize, fully depreciated processing infrastructure built over decades, and a captive domestic demand that provides guaranteed volume regardless of export price. A new Western rare earth processing facility, built to Western environmental and safety standards, must recover its full capital cost through market pricing. In competition with Chinese material priced below the Western producer's operating cost in some scenarios, this is not viable without either a. Government purchase commitments that guarantee demand at prices that make the investment viable, b. Tariff or other trade restrictions that prevent below-cost Chinese imports from undercutting domestic producers, or c. Defense procurement mandates that require domestically processed materials regardless of price differential. The United States has implemented all three mechanisms to varying degrees: DoD purchase commitments through the Defense Production Act, Section 232 tariffs on various Chinese goods, and domestic content requirements in defense procurement. The question is whether these mechanisms are scaled sufficiently to support the investment level required. The current investment trajectory, while significant, represents a partial solution to a comprehensive problem.